So over the years, you've looked at lots of different curves, and without realizing it, you've seen different characteristics. And I'm going to give you some basic definition of things that you already know, but give you some terminology. If I want to consider the idea of what we call concave up, well, what concave up means is that basically it's all the part of the graph where the graph is opening upwards, like a regular genuine parent function parabola. And so it's when it opens upwards and the graph is opening upwards, open up. So even a graph that's exponential like this is concave up. It's always going upwards. And concave down, to change to green, is when the graph is going downwards. Okay, it's going down. And so if I have a graph like this, this is always concave down, is opening downwards. And well, there is between concave up, the green, and the blue, we have in the middle here is the transition between concave up and concave down, and that is the point of inflection. It is the transition between concave up and concave down, or vice versa. So it's when it changes concavity is what a point of inflection is. And when consider, we have the sine curve. Well, it has a point of inflection, point of inflection, point of inflection, lots of different points of inflections as we go. Okay, and so then we'll go on. So those are definitions: concave up, concave down, points of inflection. If I want to consider graphs increasing, well, let me change my colors again, or get rid of this. If I'm doing increasing, that's whenever the graph is going upwards. Well, I can clearly see the graph is going up all the way here, up until here is up. And then it goes up again here. Remember, I always read a graph from right. Oh my goodness. Always read a graph from left to right. From left to right. As we read a page on paper, we read graphs. So here is increasing, increasing. If I want decreases, I mean, when is the graph going downwards? Well, it goes from here to here, it is decreasing. And so the stationary points is when the derivative is 0, and they're often where there's maximum minimums. So there's a horizontal tangent line, and it often is when there's a maximum minimum. That's not guaranteed, because it's possible to have a scenario that goes like this, and this will be a horizontal tangent line here. There's no maximum minimum. So just to recap, we got concave up, concave down, points of inflection, increasing, decreasing, and stationary points. So now let's actually look at derivatives and their slopes. So if we have our function f of x here, this is f of x, and the derivative we want to sketch, and the derivative is always the slope of the tangent line. And so if I move over to the sketch here, one of the things we have to differentiate between values of the function y and values of the slope of the tangent. Okay, and so the derivative is the value of the slope of the tangent. And right now, my slope is quite negative. And if I move a, I can start to build my derivative out, my derivative function. And as I move it along, I can see down here that the slope of this line is negative 6.92. This is 1, so this is actually the value of the derivative. So as I move around, you can start to see b is the function, the value of the derivative. And as I go along, here we go, and at this point here, the derivative is 0. Okay? And if you notice, that is where there is a minimum value, where the slope is 0. And if I consider all the slopes leading up to it, all the slopes were negative. And so now if I keep on going, I'm going to move along here. You can see that all my slopes are positive. My slopes are positive, so the y values are positive. the y values of the derivative are positive, and so on and so forth. But something interesting happens here. It was getting more and more positive, and then it starts to get less positive. Okay, and as I move along here, slowly going along, I can see again the slope line is 0, so the derivative goes through the x-axis, and the values of the derivative now are negative. The slope is negative, and it keeps on going along here, and there's also, I can see clearly it goes through 0 again, and then the slopes are all positive. And so I get positive slope, I get a negative slope here first to 0. So if I analyze the first derivative relative to the function, so when this first derivative had a slope of 0, it went through the x-axis. It happens here. It happens somewhere here-ish. The derivative goes through the x-axis. These slopes here were negative, which is referring to all these are values of negative of the derivative's function. Now if you look at the graph of f of x is decreasing. So if my derivative is less than 0, that means negative, then I know that the function itself is decreasing. If my derivative equals 0, then we know there's either minimum or a maximum. So it's a minimum or a maximum that is possible. And then when I see all these values of the derivative are positive, and that happens here, where the values are positive, and all these slopes are positive slopes. So if my first derivative is positive, bigger than 0 or positive, then if you notice this function, f of x, is increasing. Okay, and so that's what happens. So I have 0, I have the function itself. When I have a horizontal tangent line, the derivative is 0. If the tangent slopes are negative, that means the graph is decreasing. If the slopes are positive, that means the graph of f of x is increasing. Okay, so that's the analysis of the first derivative. But what's interesting is there's aspects of this graph happening that also the derivative of the derivative. So let us now consider the second derivative. And so if we sketch the second derivative from here, I'm going to look at all these dots, and I'm going to use green here, and I want to sketch the second derivative. And so if I sketch the second derivative, I know here is 0, so it's approximately here. I also know here is a horizontal tangent line, which is about right, I think it's about here. And I know these slopes here, the slope that is positive, that is a positive slope. So that means I'm going to be above the axis here, positive to here. These slopes here are negative slopes, so I'm down low here. And these slopes are positive. So the graph is going to come down here and then spin back up here kind of scenario. Okay, and so that is going to be my second derivative. So f double prime of x is in green. Well, what's interesting to me is at this, where this is 0 here, horizontal tangent line is 0, how does that relate to the original function? So if I come down here to the original function, it is approximately there. Where this one's 0, it is approximately here. And I want to look at the curvature of the original function. And if I do that, if I notice all this part here, up, that's where the first derivative goes to 0, the second derivative goes to 0. And if I also look here, I can see, and I'll also make the blue highlight, what I can see is that here, the second derivative, all these values here are positive. And so the positive creates this upward trend. And so if the second derivative is positive, okay, positive, then the graph of f of x is concave up. In this blue region here, if I look at the second derivatives, all these tangent slopes here, they are negative. If the second derivative is negative, then I have this idea of concave down. And these points where the second derivative is 0, these are where we get points of inflection. Occurs when the second derivative is 0, where it changes from concave down to concave up. So when I look at the second derivative, if it's positive, the function itself is concave up. And if the second derivative is negative, the function itself is concave down. And so this second derivative being positive or negative tells us about the original function. And this point of inflection is in the original function. So in a summary table here, I know if I consider the original function, this is before we did any calculus, original function, when it equals 0, I got the x-intercept. When f of x was bigger than 0, that means I was above the x-axis. And when it was less than 0, the graph was below the x-axis. Now, if f double prime equals 0, that means there was a possible max or minimum value. There's no guarantee, but if it's going to happen, it's going to be at these values here. If the first derivative is bigger than 0, so these are positive values, that means the graph of f of x is increasing. And if it was negative values, that means f of x was decreasing. Similarly, if I now look at the second derivative, if the second derivative is 0, there is a possible point of inflection. Now, there's no guarantee with that, because if you look at x to the power 4, you can clearly see that if this is the graph, if you do the calculus on here, this is not a point of inflection, though this is where it will equal to 0. You can investigate that to know more clearly on your own. But if my second derivative is positive, then it is concave up. And if my second derivative is negative, then I have concave down. And one of the things that I really want you to recognize is all this information here is about the original function f of x. So the second derivative tells us about f of x. The first derivative tells us about f of x. And so all this information, when we find out when the second derivative is equal to 0, we know it's a point of inflection for f of x. It's concave up for f of x, not f double prime, but all this information tells us about f of x. And this is a really handy graph to keep track of. And there is your theory for curve sketching.